right. Welcome back to Cohort 8. We are definitely in the back stretch, in the final chapter. So we'll have two discussions on chapter 5. Then these last weeks, we tend to not record them. It's usually just like looking at the feedback form, giving people an opportunity to fill out the feedback form. I'll update the numbers. And then just looking at a lot of the thoughts people have had about future textbook groups and just as we get further and further from the initial book and sort of explore other reading groups. So they're just fun. And then that kind of closes this phase. Then we'll probably resume with chapter 6, but for in some months. But first, let's go to and one other uh piece I just wanted to show initially, Sanjeev Namjoshi, who's the author of the soon to be published The Fundamentals, two textbooks with one of them coming out. Um, he has also made an open source repo that I'm just running it right now locally, and this is what it pops up from a Docker container. So that's kind of like veering from the textbook group, but all the different references and things that people bring up and just and it's also a cool place to explore like literature meta-analysis and other kinds of literature-based methods. Okay, chapter 5 though. Would anyone like to start with any recap of 5 or a question or section from 5?
I found it, I'm Andrius Kulikauskas. I found it very helpful just in terms of making sense of active inference in terms of domain. And maybe this is the domain where it was first recognized and formulated. And so, which is neuroscience, brain sciences. And so, for me personally, they make a note about the relating of the discrete models with the continuous models, how that functions. And so I think that there's something more to be discovered there. And then I guess there's this theme of message passing. So that's a code word, I think, for neurotransmitters, saying that you can model neurotransmission with Markov processes, and thus active inference becomes relevant. And then there's also examples with the cortical columns in the cortex, trying to make layers and how are those layers act. And so, uh, or I'm also interested, like in the subcortical structures, like the basal ganglia. You have excitatory, I think, direct pathway and inhibitory indirect pathway that are connecting with motor capabilities, sensory. Very helpful. This idea that you need to, with precision, of the understanding, I guess, of the, let's say, sensors, the proprio sensors, I think, um, sensors like where they need, if they think that they're not moving, they're not ever going to move. So you have to make them doubt whether they're static, and then you can let them think, oh, you're moving, and then they start to move. So that's a very interesting dynamic. I think that that really helps to um, I think it is just it helps to think about what's going on, and then that makes active inference intuitively an attractive framework, and then mathematically interesting. How helpful.
Thank you. Great comments. Anyone else have like a section or a comment on 5?
I'll just say more like that. It really opens up a lot of things to think about. And I think also it makes clear that active inference has something, this very important idea that,
Lost you for a few seconds, Andreas. Okay.
yeah, and
Okay,
two
can you
flavors of the same thing. And so that there's free energy principle can be understood in either, can get either one of those going. Um, but it also shows like that there's a lot there. It's just a tool for thinking about these things. But as far as actual implementation, interpretation, there's a lot that it doesn't really do for itself. You have to kind of like come up with a picture or a model or idea. And so one of the things that fascinated me was just appreciating, oh, that there's this whole language of neurotransmitters. There's this whole alphabet, let's say, of possibilities. And I don't think active inference directly speaks to what they mean. It just kind of explains some of the framework for that language. So that's what I inferred.
Thanks. Great comments. Yeah, wow. There's a lot it doesn't do for itself. That's kind of a function of the generality. And then like the table of neurotransmitters and these specific systems, this is where the sort of specific experimenting, hypothesis testing, falsification, it's like we're not seeing any evidence from lesion studies or from this C. elegans model and this mouse model. We're not seeing evidence for this cognitive function in connection to that one. So that's kind of a neuroarchitecture agnostic way to frame it. Like we tried to apply this Bayes model to these different, and we found that there were these different structural models of parameters in play. And then it could also connect with a more explicitly mechanistic research agenda, like arising from SPM and the empirical work on fMRI and neuroimaging, where they take similar models to these and look at how these parameters differ, keeping the edge constant, or look at how certain parameters differ under different structural hypotheses, like in attention or unattended context. That's kind of the SPM, fMRI, EEG classic studies, which are kind of explored in chapter 9. So it's like chapter 5 is the first time that we're encountering the specific um, cognitive in a continuum to neuromechanistic hypothesis, falsifiable, um, drawn from larger possible hypotheses. Like if the even just keeping the same variables in play, there are other structural hypotheses that we could imagine. And there might be a given area of phase space, could be small area, could be a huge area, where like two structurally similar models are can't be one can't be said to be like better than the other. Like they're not identifiable from each other. And that comes up with like structural equation modeling in just any kind of statistical method. Um, Anyone else want to go to a part where we could try to look at one of the papers that are cited for more information or look at one of the three subsystems more? Yeah, Sylvia.
Um, I do have a part that I've been thinking about, haven't really got to my head around. It's page 95. So section 5.5. At the bottom bit of that page, it says the relationship between the two is simple. If we have very precise beliefs about how data are generated from hidden states, then our beliefs about hidden states can be updated by observing data more than if we are not confident in those beliefs. I'm just wondering why isn't this the other way around? As in, if you are less confident that you might have to update more.
Got that same exact question. I'm glad you asked it.
Yeah, it is a good question. So, two cases. One of them is the prior looks like a very broad Gaussian, like it's 10 plus or minus 5. And then a new observation comes in. So it's not a very precise belief. New observation comes in and kind of shifts the whole Gaussian slightly. That's a low precision belief updating slightly. If there's a high precision belief, then it's like a 10 plus or minus 1. And if that same measurement of 14 comes in, the posterior could move a lot to that. Now, whether the wide high variance or the low variance prior moves not at all or the way is like an attention precision question. So I think here, it just looking at all other things being equal, Bayesian updating, I think that for the same attention, the tight distribution would update possibly less because the observation is just so unlikely. So it's like the posterior might not update that much, but maybe because here they're focusing just on the precision,
Can
but
I,
but it is separable from seemingly from like what the actual variance of the target distribution is. Whereas if you believe that it's an informative channel, you update more.
can I give an example and you see if
Sure.
it's right? Yeah, so let's say I'm wondering where my brother is. So one very vague idea, my brother went out. A less vague would be my brother went out to the store, and more precise would be my brother went out to 7-Eleven. So you see, if he went out to 7-Eleven, it's easy for that to turn out to be needing to be updated. Lots of things could say, well, he's on the other side of town, right? Like so, but if he's on the other side of town, he may still have gone to a store, right? So the more precise it is, the more easy it is vulnerable to, being affected by more information.
Uh,
That's the way I'm reading.
I I
Or am I
I
wrong?
I I think that's related. I hope I'm not like over splitting it, but it's like let's just go with the 7-Eleven case. So there's three people in the room you could ask. And they're going to tell you at those three levels of coarse graining of location, like the tens place, the ones place, or the decimal place, or all three. But then attention would be on a 0 to 100, a 0 to 1. How much are you going to update to that belief, including not mattering at all? Like if you already believed that he went out, then 0 or 100 attention to the person who's going to tell you just that isn't going to update your belief at all, whether you're paying attention to that first person or not, because it's like the ball is already at the bottom of the bowl. It's already at the maximum likelihood solution. Whereas, if you had 100% belief, you're going to update to just whatever the person tells you. So that's so it's like the or just like the proprioception coming from a hand. Like that little corpuscle or unit could be firing madly or not at all, or anywhere in between. Now, that could have any relationship to whether there's like actually heat or something. So that's whether the three people in the room are telling the right information. But then there's the attention to that. So if there's precision, if we have precision on the A matrix, which still could be ambiguous or not, then beliefs about hidden state can be updated by observing data more. So it's kind of like scaling the impact on the Bayesian updating of the beliefs about hidden states from attention to the observation.
Can you elaborate on the role of attention in relation to precision again, please?
Yeah, I think attention and precision and temperature sometimes are used in sort of um, similar-ish ways. But even like the attention in the transformer, like this is kind of a super built out version, but in its most um, single parameter setting, it's just like how much impact on the latent state it is being influenced by the new observation coming in. So like complete attention is updating all the way to the new data point. Like someone says, it's 4. You go, it's 4, and then it's 5. Okay, it's 5. So it's now that could have whatever variance. That's whether the object level distribution is just has a given variant, small or a large variance or whatever, or it's a Dirac delta function. So it's just single parameter. Like there's no variance. Um, and then no attention, which is kind of one of the multiple places with attention, confidence, belief, where it's like a psychological term moved into stats, now coming back to confusingly either apply or not apply to that psychological phenomena or be some other psychological phenomena. But it's like if something is not paying attention at all, the other extreme, it doesn't have an impact on it learning. It was functionally didn't happen. So that's like if um you have some A matrix, the ambiguity matrix mapping observations to latent states. So it could be like a uniform distribution, which just is like the symbols coming over the channel don't reduce uncertainty about the hidden states. Or it could be like an identity matrix with just the symbols coming over the channel have complete concordance to this latent space, or other matrices in between. So that's about like the kind of object level properties of the mapping between the observations and the hidden state in the values of the A matrix. Um, then, uh, and that could just have sort of a implicit kind of attention of one. But if you wanted to explore different impacts of that mapping on belief updating or have modulation within a model of how even uh, those beliefs impact updating, um, having another kind of like a volume knob parameter that can go between this channel is not having any impact to this channel has a high impact is kind of a common mechanism. So sometimes it's done with like a 0 to 1 just type scaling. Sometimes it's done with like more of a just other ways. And then even though it's a little bit different, here's where there's like a temperature. Um, just scaling different variables because that's kind of one of the ways when it gets down to the calculation of it, that's like how these matrices can come to have different impact on each other is just through scaling them, like by a coefficient, or raising or lowering them to a coefficient.
Thank
So
you for that.
here's
Sorry.
multiplicative weight is a coefficient.
Right. Right. I guess in terms of math, it can be understood more intuitively. Um, so is it fair to kind of understand this as, I don't know, the update will be reducing uncertainty and our beliefs about hidden states can be updated by observing data more. In that, it's kind of like you become more certain about something, hence you become more confident in that belief. And that's why it's more than if we are not confident in those beliefs.
I think it's the belief in that stream of data. Does that help? Because I think that's what I was getting kind of tripped up because I just kept thinking, okay, there's a generative model that is modeling, whatever that hidden state is. And so I'm pretty sure I know what that thing is. And then so why do I need all the precision of that channel? But it's almost like I think this is really about a belief or a prediction, maybe a model of whatever that is coming from that observable data as opposed to whatever that thing is. And I don't know if that makes sense. So it's like confidence in whatever I'm going to get next. It's almost like this if there is a model here, it's like it's a model of whatever is passing that message up. And I could be wrong about that, but I don't know if that helps or if it's accurate.
Yeah, just one to Sylvia, then Andrews. So here with the multiplicative updating on prediction errors. So it's like, let's just say that two entities are in a 0 to 100 action, a belief space, which could be a belief about action, like how likely they are to do something. So that's a huge benefit of having direct beliefs about action as opposed to like a reward function. Is talking about latent states, could be talking about a sense-making latent state, could be talking about an action inference. So that's one benefit that's not really mentioned here. So now the observation comes in, like it's a temperature 0 to 100, and then there's a 0 to 100 action space for a heater. And so one entity might have the thermometer reading comes in 5 units over their belief. So just at the pure error calculation, they're 5 points off. But then one agent's attention to those 5 kind of raw units of like that, those are the units that are kind of getting pumped through the A matrix because it's literally where the observation from the thermometer is meeting the latent state beliefs about temperature from the agent. But now at the attention level, one of those agents could just turn that 5 into a 0.5 by having 0.1 attention. Another agent or another context for the same agent could have a 10 attention. So then it's like 50 units of surprise. So that's the difference between the same 5 thermometer units being for the purposes of Bayesian updating, like it could be like a 5 sigma update or a 50 sigma update in terms of how surprising the event was. Andreas.
Yes, I'm thinking intuitively like about a scientist with a hypothesis, and this notion of confidence, and I would also relate that to specificity. Like confidence can mean two different things. Confidence can mean like a moral state, like are you taking a stand or are you not? But I think here, first of all, it doesn't mean anything like that. It just simply means, given all the options, how specific are you, that it is a certain way and not other ways. So like when things are very vague, that's in a certain sense, that's not having confidence in anything. It's just saying, or it's not specific. But if you're a scientist with a very specific hypothesis, that can be inferred that, well, your confidence is in that very high, and your confidence in everything else is very low. So when you have a very clear, specific hypothesis, quote unquote, get your confidence in, then you're really subject to updating because there is something to update. But if you don't have anything specific, you don't really have implicitly any notion of confidence, and there's nothing to update no matter what you discover because you haven't taken any position or any stand. So that would be, I think, if understanding confidence just simply in this kind of default way, then the whole other notion would be, well, what would it mean to have an extra notion of confidence where you can choose to be more invested or less invested? But then that would be a whole separate question. I don't think that that's the matter here, but
That great
yeah.
example, Andreas, and a great example. So it's like there's two rooms. One of them has a uniform distribution of temperature. One of them has a hot spot. Now there's two investigators. One of them has a uniform belief about the space. The other one has this hotspot concept, like they're fitting a Gaussian or they're fitting a Dirac delta function to the room. So it's like in the flat temperature room, that sort of flat hypothesis um is the right one, and there's no reason to pay attention. But even paying attention or not in that room would keep it the same. Whereas in the uniform room, if there's an investigator who is going to really be paying attention to their updating, then they could be updating, they could just be wildly moving that small Gaussian around because they had high precision at that level of updating. So it's just like there's all these kinds of examples help separate out, like there's like the volatility of the environment, the volatility of the updating. Then there's like the actual dynamics of the environment, and then the relevance or the accurate or veridical nature of the agent's perception. Or this kind of question of like, does it learn other features? Like the whole kind of Hoffman angle with just the evolutionary game theory of learning cognitive structures that, surprise, surprise, are not the exact structures in the world.
Yeah, those examples make perfect sense now. Thank you. Thank you for the explanations. It becomes very clear with those examples and put that into context.
Thank you. Yeah, there's a lot of statistical degrees of freedom, even in a linear regression type. Even just in the model itself, not even getting into the kind of like hypothesizing after results are known, like the HARC um type, like iterative inquiry or just modifying aspects of the statistical model, but just within like the POMDP that from chapter 4, or within a graph with not that many variables like this, it's like first just the which pieces are on the board is already a choice. Then there's all the connections, and then those connections can be structured different way, and then those connections could be kind of just taken in their plain first order sense. But in a Bayesian setting, if you have just a plain first order variable or matrix, it's like a constant. So that might be fine, but then it is not necessarily learnable. And even if it were a constant, there still might be another more attentional variable connected to it. One
Question.
benefit of Bayesian models in
Sorry.
this setting, just yeah, last point, and then MB, is in hierarchical parametric linear modeling, like explored in SPM, you can only test strongly models that are like strictly nested with each other. So you can test if you do the ANOVA, just normal scientific statistics, like you have the fMRI data and then you have their age and their weight. And then you can like test for, factor A, factor AXB, factor AXBXC. Um, you can test those as nested ANOVA, and then you can say we found evidence for an interaction between the fMRI and age, but we didn't find it for weight. So that's the way you can do the structural hypothesis testing within parametric classical stats. In Bayesian stats, you can use Bayes factor and other just sort of empirical methods to just select models based upon their fit, and they don't need to have a structural relationship to each other. Whereas in the linear statistics, it's more constrained, but it's a more simple test. And that's why there's just so much similarity in ANOVA methods. And the SPM textbook has a lot of this information. MB?
Thanks. Yeah, I am just curious about the model itself. So, to use Andrew's example, which I thought was great, I'm a scientist and I have a high degree of confidence in my data, right? And so I have a hypothesis, and my hypothesis is confirmed by the data. And so I can see how there's high precision, but that would be to me, that would seem like a very low model update as far as the magnitude of the update. Am I thinking about that in the right way?
Yeah.
Okay. So
Someone could
then
have a
I could also see,
high precision ambiguous view. I'm sure that it's
okay,
ambiguous. Or you could
yes.
have a high precision, low ambiguity view, like I'm sure it's this way.
Hmm. Could I also, I could also see how I would have, as far as the general model about whatever that hidden state is, I could say, I have no idea what that hidden state is, but whatever comes in this channel here, I'm going to believe. So that's like a probably a huge belief update, right? Like I have no idea what's coming. Whatever it is, I see. I'm definitely buying it, right? I believe it.
Yeah,
So
that could be
I guess it
you do
doesn't have to
slot
do with
machine.
the
You do slot machine.
sorry.
You really don't know if you've won, but the first observation that comes in on roulette, you're just going to have 100% updating to whatever it is.
Uh-huh. So I guess it's not really about the certainty of the model itself, it's the certainty of the data. And I think that's the whole point of this, right? Is like we have very precise beliefs about how data are generated. Then so it's really not necessarily about the uncertainty of the models. It's that second level prediction. Is that right?
I, I think you're raising the sort of human model interface of how much trust is in that model or attention to that model. But yeah,
Mhm.
within the model, what the attention so not the human's attention to this model's output,
Mhm.
just within the model, it is
Mhm.
it's like a scaling coefficient on blurriness of input, where you can blur a channel to just basically be in the backdrop of nothing, or sharpen it to a high layer.
Can I jump in?
Yeah, go ahead.
Yeah, MB, I think I disagree with you. And the first thing is that I think there's two completely different notions of confidence at play here. One that I think it's natural for us to be injecting, which would be like human personal belief. I don't think that that's implied here. I think all they're saying is that when you have a distribution, because they're talking about any distribution, as soon as you have a distribution, if it's peaked, you're implying that you have confidence in that particular zone as opposed to the other zones. If it's flat, horizontal, then it's just implying you don't need confidence in anything. I mean, and just the shape of the distribution indicates a certain type of implicit confidence at play, which has nothing to do with mental states or, like our personal beliefs. It's evidenced by the activity, if it's evidenced by the distribution. So if you are a science, and if you have just intuitively to try to understand, like if you have a clear hypothesis, you can be wrong. If you don't have a clear hypothesis, you could never be wrong. You don't have a problem with being wrong. If you're not going to be wrong, you don't need to be updated. If you can be wrong, you are at risk of being updated. And so I think that's the issue there, is that the more clear and specific you are, the more you will be open or vulnerable to being updating yourself. The more vague you are, the more kind of like you frame what you say, the more you just kind of make it all mean nothing, the less that you have to worry about updating.
Although being very precise in your beliefs, but having no attention to input does not lead to updating either. So it's not simply that having precise beliefs
But that
about a given
that's what I'm
state.
saying. Like, there's these two notions of confidence at play, which I think has to be first. One is, and so the idea of attention. See, attention works with both versions of confidence, but I think the version that they're talking about attention is simply the fact that if you focus on anything, without having any mental apparatus like a human being, but any kind of system that has some kind of focus is going to, as soon as you focus, you have an implicit notion of confidence. And if you aren't focused, you have an implicit of not really having confidence. So, and the implicit, implicit, and maybe to kind of push that further, this whole distinction between the discrete world and the continuous world, like you have these continuous actions, they have a notion of confidence, like a specific action, that was taken. Where there's no mental belief, but it's a specific action. But also, like in modeling that with our generative models or our like finite models, like we have also can have a notion of a specific thing, or maybe even a confidence value. I don't know, but I'm trying to deconfuse. I don't know if I am.
Yeah, I hear you on that. I think there's probably ways to write out and program all these things. And again, there might be situations where these models have the same directional, just they capture the same variance, or there could be some contrived example or some pattern where they capture different elements. But it's like, but again, that makes it clear. So there's the investigator with precise or imprecise beliefs about the room, about whatever their hypothesis is actually about. And then they could be paying attention to the thermometer or not. And then but that can look so many different ways, just depending on what the state spaces are. Because also, like, beliefs on an information channel, it is a latent state. Like, if we have it's like we're going around the room with the thermometer, and then there's some unobservable in the room which relates to how variable the thermometer is. That's like the recurrent switching linear dynamical system in the RxInfer. It's like there's a 0 or 1, there's two underlying discrete dynamical states. Just two states that just are doing this function. And then they switch between a low and a high variance mode. But you're only getting these observations just as the raw data points. And then this could just as the variance estimator changes, you can infer that you're in a different latent state. So these aren't so different. And partially it's because people use latent state to sometimes mean just environmental states. But when you get into the model, it gets more specified. Sylvia?
Yeah, I thought of an example just from a computational psychiatry point of view. If we think about people with maladaptive beliefs or some sort of psychiatric condition that may then have like negative beliefs about the world, and more often or not, their beliefs are very, very precise. It's too precise, even though it's inaccurate. And the reason that they are not really updating that belief is that they will actually purposefully ignore certain data that would challenge that negative model, the negative belief, or they will selectively just choose the things that will confirm that model. And that's why they will appear to be trapped in that belief. I guess that would be an example for the differentiation that you mentioned about on like whether you pay attention or not um, to that data.
Yeah. There could be a lot of ways that in a complex model it plays out, but like precision on how informative 0 to 100 beliefs on the screen are taken to be. And then there's like the epistemic foraging of choosing where to look. Whereas in a lot of these textbook type examples, it's like the agent is just kind of locked into the one stream of information. And we're just talking about the dynamics of one stream of information coming in, like the sequence of music notes. But once you start getting into like behavior switching or location switching, that is whole different spaces of what information to choose. But it's like everyone selectively chooses information. And some would probably even extend that all selectively choose information to confirm their model in the kind of self-evidencing maximalist take. Um, John and then Andrews.
Um, if you talk about the information coming in, you have to somehow figure out the mutual information between what you're seeing and what you want to know, and that in general is a very hard problem. So how do you evaluate that someone else has, um, you know, what's it called? I don't want to say psychopathology because that means something specific, but pathologies of the mind. How could you tell from the outside? Because you have to know the mutual information, and that's typically very very hard.
Yeah. Short answer, um, empirically, the mutual information is you're gonna call some computer programming like package, like mutual information between these two distributions. So there's more to like what is the actual mutual information or what is actually happening, but just at the sort of really pragmatic level. Mutual information is also going to be conditioned upon what model you have. Like if your model is just a coin flip, then you're only going to be able to get one bit of information if you are maximally imprecise about your belief. Whereas like, if you had different beliefs about the coin flip, then you might get a different amount of information from it. But that shows just quantitatively, um, the mutual information is about the distributions in the model. So then you can look and infer different parameters in your model. You fit your model to data, and then you look at the parameters of your model and their variance profiles, whether you do it with classical, like parametric statistics, or Bayesian statistics, or non-parametric, like sampling-based methods, you're going to get some graph that looks like this. This could be like the risk score of 5 different properties. This could be that some cognitive parameter for 5 different entities or 5 different contexts. So that could be wrong, but that is your calibrated and empirically driven belief about a latent parameter reflecting some cognitive phenotype of interest that you explicitly specified.
Right, but I just don't see how you get out of this situation of your model's pathological. No, your model's pathological. You don't have the mutual information. No, you don't have the mutual information.
Oh yeah, yeah. I mean, there's two. Yeah. Okay. So now we have two modelers meet, and they're drafting the DSM or they're drafting whatever, and then and then even on the same model, one could say, well, the threshold for this or that should be 10%, or it should be 2 sigma, or it should be this. It's like debating where's the threshold and what to do with model outputs for the same model. That's a thing. And then debating which model, that is another space of discourse. But just within a given model's output, those yield beliefs on latent state. But what you do with these risk estimates, or how you made and how you selected your profile of risk modeling models, that's not just like you just make one and just take it. Axel, then Andreas.
I think Andreas was first, so you can just
Okay,
go ahead.
yeah, good.
I'll jump in. I think Sylvia's example relates to the whole basal ganglia issue about how can action be changed. And I think that belief changing may be very similar, like to changing the state of action. And this would relate to John's issues regarding, objectively talking about pathological thinking. So active inference is very incomplete in many ways, but with regard to this specific type of issue, it's suggesting that if you want to change action, you need to lower your precision, in terms of your understanding of what the current state is. Otherwise, you'll never be able to get out of it. You'll be stuck in a rut. And similarly, like if you want to change your beliefs, you have to be able to let go of your precision and reduce it down so that then you could reevaluate and reclaim it or to change it. And so if you don't do these things, you'll never be able to change your state of action. You'll never be able to change your beliefs. And it could be said like there's a pathology in that, in the framework of active inference. And there's probably, there's examples, I think, of where you can see that neurologically, but it's just a general mechanism.
But there are approaches where people say the fact that I never update my beliefs is what makes me right, and
Yeah.
if
So
we're
that
all just trapped in the world of probability, it's hard to.
Well, so there's a virtue to having very strong beliefs. So let's say I believe in God, but if I insist that the name of God is, Joseph on Thursdays and Mary on Fridays, well, am I willing to let go of that belief and reclaim it? You see, like not let go, but like to attenuate it. If a person's not able to attenuate it, that means that they're not able to change beliefs, then it's not clear why to have beliefs, like why be alive in the first place. So I think it's just saying like if you accept active inference as a theoretical framework, why well
But I
then
think
these
the idea is they would have the beliefs because there are preferences that are adaptive, right?
There just is a lot of pieces. Again, it doesn't necessarily need to apply
yeah
to this like self-understanding of life at all. This just can be understood and possibly more formally, accurately, just at the level of variables and the relationships. But there are some intriguing parallels. But just I don't think every single analytical relationship needs to um map to any given psychological one when they're simple motifs. But those are all examples of things that deploy this simple motif in intense ways. Axel?
Yeah, thanks. So I have a question which is much less related to chapter 5 and also less related to these philosophical discussion. So I don't know if it's actually better to bring up in another meeting. If it's more like practical implementation of active inference. But yeah, I can ask if no
Yeah,
one else
just
has some
yeah,
additions.
just go for it.
Sure. Maybe if I could share my screen, would that be possible? I can just show what the problem is.
Sure, go for it. There is only
Great.
8, but yes, go for
Yeah,
it.
sure. I'll go fast. So basically, I'm writing my master's thesis right now, and I'm very interested in trying to combine causal discovery with active inference. So causal discovery is basically, you have different nodes. You could have a causal graph that says X causes Y, which causes C, and you're trying to find out the true causal structure. There's a lot of literature on this, but I thought it was specifically interesting to use active inference for this, maybe specifically for intervention selection. So for example, let's say you have all kind of different variables, and you have to figure out how they relate to each other, what causes what. Sometimes you'll have to intervene on certain variables in order to learn something. So kind of with this example here, you wouldn't actually from observational data be able to distinguish between, let's say that X and Y and C are all covariant, but you don't necessarily know if it's Y that causes X and causes C, or this other one. So in order to figure that out, you have to carry out some interventions. And I'm kind of trying to do that with active inference right now. And I was hoping that maybe some of this kind of reducing uncertainty and minimizing free energy could be used to maybe choose the interventions that were the most like reduce the uncertainty the most, and that would be interesting. I've set up kind of a simple example here where I have a true causal graph, which is this one. And here my states have become all the possible values that these different variables can take on. And I have some probabilities over actions. And I start out by just having my B matrix complete. My A matrix basically is known. It says, okay, when the observations are the same as states, when all these variables are 0, 0, 0, I will see that they are 0, 0, 0. And then I have my probabilities over actions where I am able to do no operation. So I'm not intervening at all. I can intervene on X. This is basically like toggling it. So if X was 0 and then I intervene on X, it becomes 1, and so on. And I run through this example, and I have my C, like I start out my prior D, I start out in this 0, 0, 0 state. My desired state is to be in this second to last state where X is 1 and Y is 1 and C is 0. And then I kind of start out and I run it, and it says, okay, it starts out by having an equal probability over all actions. I try X. This takes me to the final state because X causes Y to be 1 and causes C to be 1. And let's see here. Now I'm in this final state. And again, I have equal probability over the actions because I've never been in this state before. And maybe just to go a bit quicker over it now, because we don't have that much time, what ends up happening is that I keep getting into these different states. When I haven't been in a state before, I haven't learned anything about where my actions will take me in the B matrix, so therefore I'll have even probability. It takes a pretty long time before I finally get around to getting to the, let's see here, the desired states, which is, I have it here. So I get to the desired state here, and now you'll see that because it's okay. Now this is, of course, always with demos, it doesn't work, but basically I end up getting to the desired state that I want, which is this state right before, and then I just keep doing no op. But it takes me a very, very long time to get to this place. And I'm wondering if just quickly, and maybe anyone else also has some ideas on this, whether active inference has been used for this kind of causal discovery before, and whether one could learn the causal structure in less time. Because right now it seems that my big problem is that I maybe learned that no op doesn't change anything, but I only learned that in the first state. And then I have to also learn that it doesn't change anything in the second state, and the third state, and the fourth state, and so on. And yeah, I was just interested in any input on that and any thoughts, if anyone had some.
Yeah, great work. Definitely cool to see that kind of direct active for the causal discovery. Um, when you are initiating these new slices,
Hmm.
there are heuristics that could um, accelerate and transfer the learning. Like if if we have a room with all these locations and then we have the heater and the cooler, we don't need to learn that the heater. We don't need to have a flat prior on what the heater does at every single square. So like instead of
Hmm.
initiating as a flat um, belief when you were bringing in these new blue ones, they could just take the average of the other ones.
Okay.
But there's kind of no free lunch because you could then you would be you could there's a situation where that will learn fast if the relationships are transferable. But if they are,
Right.
then do we not initializing the matrix with like the rows or the column or whatever averages, or just or however other just initialization heuristics can go really far.
Hmm. Would I be able to find this somewhere? Has this already been this kind of averaging, or are you just coming up with this now?
I don't know what specific paper, but I've seen it in just regular statistics and ways of
Right.
doing.
Okay, interesting. And then just maybe one final question. So another way right now, the way that I'm setting it up is that I'm basically the states that I have are the true combinations of all values that there could be. Another way of framing this is that instead of doing states as the values, I actually do the hidden states as the true causal structures. So, for example, I say one state is X causes Y, the other is that X is caused by Y, and maybe they're independent of each other. Are the three different possibilities in this example? But if you were to do this, then my hope would be that you would finally learn the true hidden state, right? Which would be the true causal structure. However, I'm a little bit unsure about what would the observations be for this, right? Especially because the observations in the data would be the same for at least this and the
Yeah,
first one and the second one.
that's like the simpler MDP case. Like if you want to just do away with the partially observable part and the whole observation to latent state mapping, it's like just working within the latent space because
Hmm.
observations and the latent states are the same.
Hmm.
Sometimes people do that. Other times, still have the A matrix, but just make it an identity matrix. So
Hmm.
then you still get to use observations and have a separator, which could later be fuzzed, but you can start with just passing it through basically.
Right. And would the B matrix then be useful at all? Because I'm thinking, for example, here, I mean, the way that I would learn, like let's say the way that I would learn that X causes Y instead of the Y causes X is that I would, well, this is very thick. I would carry out an intervention on the X. So I'd say like do X, set it to 1. And then maybe I would see that if Y changes when I change X, when I carry out this intervention, then I would guess that I'm in this state. If Y doesn't change when I change X, then I can infer that either they're independent of each other or Y causes X. But then I feel like I would have to create an A matrix for every single intervention. Then I have to say, okay, if I have if I carry out an intervention on X and I see that X and Y are independent, then I know that I'm in one of these two final states. If I see the white changes, I know I'm here. But that it seems I'm getting a little bit too far away from what active inference is if I'm creating like many, many different A matrices. Or what do you think?
Well, one answer is it just depends on whether you're continuing to do a variational or expected or other free energy. Like if you're still doing
Mm-hmm.
policy inference with EFE on the B, then these are just and then it's just what question are you really trying to ask? Like, are you in a situation where the causal structure is fixed and the agent is inferring it, or can there be switching of the causal structure? I mean, or just
Mm.
what, or can the agent act to change the causal relationships, or only just kind of poke each of them to give an output? And that's kind
Right.
of like the dynamic causal modeling setting that again SPM kind of led to, which is taking in noisy EEG fMRI data and then asking what is the effective connectivity in a structural dynamical causal model of these brain regions. Like, is there any causal influence of the implicit neural activity proxied by the bold on these two regions? If so, what is the dynamical structural model for them? And
Right.
then they show in the textbook, and like this is kind of like why I come back to it, because it shows here's how it's done with generalized linear modeling with parametric classical stats. Approach two, here's how it's done with Bayesian statistics. Here's pros and cons of doing variational inference. Here's pathologies and heuristics for priors. And then third way, here's how it's done with non-parametric statistics like bootstrap, resample, which are like non-parametric. But
Mm.
so just the all those tools really well worked for the brain imaging setting where there's this like high dimensional, noisy, lagged, proxied fMRI measurement.
Mhm. But do you feel like is there an intrinsic motivation in the active inference framework or drive to learn the causal structure? Because in the examples I showed you before, I was telling it that my preferred observation was to be in a certain state or have a certain observation. In reality, I don't have a preferred observation. My preference is that I find the true causal structure, right? So it'd be very hard to kind of say that there's a certain observation I want to see. And that's why I'm trying to maybe change the framing a bit. But I don't know, maybe John, he has some
Yeah, last
input.
comment, but yeah, I
Yeah,
hope you
yeah,
share
sorry.
more and we can discuss it more.
Yeah, I have
Yeah,
a question for Axel actually. So these X and Y, are these propositions or are these like states in a phase space?
right now they're just states. Right now they're binary. So X can be 0, 1, Y can be 0, 1. Very simple setup.
So they're Boolean, so they're propositions, would you say?
Yeah, you could say that. Well, it looks like
All right.
Y, X implies Y, right? But it is kind of saying that X is causing Y. So if X is 1, Y will also become 1.
Yeah. And there's just there I'm gonna just end it just because we're already past the time. But there's
Sure, sure.
a lot of cool work with causal nets and Petri nets and all these kinds of things. So thank you though for
Mhm.
sharing that. All right.
Yeah, thanks so much for the input.
Thank you all. Bye.